Here is a question that sounds stupid, but isn't. If you turned off every star in the universe, if you crushed every galaxy, would it be dark? Most people say yes. Obvious, right? Black holes are black. They eat light. They are the definition of darkness. Wrong. Not just a little wrong, fundamentally, catastrophically wrong. See, we are told that black holes are cosmic vacuum cleaners, that nothing escapes them, that they sit there, invisible, waiting to swallow you whole. But the universe doesn't care about what you were told in high school. Here is the truth. If you take a black hole and shrink it down to the size of a single proton, it doesn't vanish. It doesn't sit quietly. It explodes. It flashes with the brightness of a billion suns. It screams. It releases more energy in a microsecond than our sun will in its entire lifetime. Black holes aren't the absence of light. They are the most efficient engines of light in existence. They are batteries waiting to go off. And the reason why? It has nothing to do with gravity and everything to do with empty space. You think empty space is empty? Let me show you. To understand why a black hole shines, you first have to understand why it shouldn't. You have to understand the trap door. In physics, we call this the event horizon, but that's just a fancy label. I want you to visualize a waterfall. Close your eyes and imagine this. You are in a canoe, paddling down a calm river. The water is moving slowly. You can paddle upstream if you want. You are in control. But as you get closer to the edge of the falls, the water speeds up. At a certain point, the water is moving faster than you can paddle. It doesn't matter how strong you are. It doesn't matter if you have a motor. If the water flows at 20 miles per hour and you paddle at 10 miles per hour, you are going backward. You go over the edge. That is a black hole. But instead of water, it's space itself falling inward. And instead of a canoe, it's light. The water, space, flows inward faster than the speed of light. Since nothing goes faster than light, nothing can paddle upstream. If you shine a flashlight out from inside the hole, the beam tries to fly out, but space drags it backward. So, logically, if light cannot get out, the object must be black, perfectly black, 0% brightness. This is what Einstein's general relativity tells us. It says a black hole is a one-way street. Things go in, nothing comes out. It is the ultimate trash can of the universe. But here is where your intuition fails. In 1974, Stephen Hawking looked at this perfect trap and realized something disturbing. He realized that if you strictly follow the rules of quantum mechanics, the black hole isn't the problem. The problem is the empty space right next to the edge. We think of space as a stage. You take away the stars, the planets, the atoms, and you are left with a boring, empty stage. Wrong. That stage is not empty. It is alive. It is violent. And it is about to break into the black hole's bank vault. Look at the space between your eyes and this screen. Right there. The empty air. It looks calm. It looks silent. If you take away the air molecules, you assume there is nothing left, just a void. Stop. That intuition is wrong. In the quantum world, there is no such thing as empty. The word doesn't even make sense. If you could zoom in, way past the atoms, deeper than the protons, down to the pixel level of the universe, you wouldn't see a flat black canvas. You would see a boiling soup, a storm. Here is the rule of the universe. Nature hates zero. Zero is too precise. You cannot pin the universe down to exactly zero energy. It violates the rules of quantum mechanics, specifically the uncertainty principle. The fields that make up reality are constantly jittering. They wobble. So how does empty space wobble? It cheats. Here is the part nobody tells you about nothing. Empty space is constantly borrowing energy from the future. It borrows just enough energy to create two particles, a pair, one particle of matter, one particle of antimatter. They pop into existence out of nowhere. Pop! They exist for a billionth of a trillionth of a nanosecond. They look at each other. And because matter and antimatter are opposites, they snap back together. Bang! They annihilate. They destroy each other. The energy is paid back. The debt is settled. The account returns to zero. Pop! Bang! Gone. This isn't a theory. We have measured this. This is happening inside your coffee cup. It is happening inside your eyeballs right now. The vacuum of space is a frothing, violent sea of particles, living and dying in the blink of an eye. We call them virtual particles. Now, usually this doesn't matter. The loan is taken and repaid so fast that the universe doesn't notice. The balance sheet stays at zero. It's a victimless crime. But what happens if you commit this crime right on the edge of the trapdoor? What happens if you create a pair of particles right on the event horizon and something pulls them apart before they can destroy each other? Then the debt cannot be paid, and the universe has to balance the books. Okay, imagine you're standing on that waterfall again. You hold 2 tennis balls, one in your left hand, one in your right. You lean over the edge. Just as you open your hands, you pull one back, you catch it, but the other one slips, it falls. This is exactly what happens at the edge of a black hole. Remember those virtual particles we just talked about, the ones popping out of empty space? They always appear in pairs, like twins, positive and negative, matter and antimatter. Usually they snap back together instantly. They cancel out. But what if a pair pops into existence right on the event horizon, right on the lip of the falls? One particle forms just outside the hole. The other particle forms just inside. Or maybe they both form outside, but gravity grabs one and yanks it in before they can crash back together. This is the moment the universe cheats. Suddenly the partners are separated. The particle that fell in is gone forever. It's trapped. It can never come back to cancel out its twin. So what about the other one, the one that didn't fall in? It's stranded. It's alone. It has no partner to annihilate with. It looks around. It can't go back to being nothing. It's stuck being something. And because it's on the outside edge of the black hole, it's free. It shoots away into space. Think about this. To you, watching from a spaceship far away, what did you just see? You saw empty space near a black hole suddenly spit out a particle. You saw radiation. You saw light. You saw the black hole glowing. This is Hawking radiation. But wait, that sounds impossible until you see the trick. You're probably thinking, okay, so the black hole is just spitting out free particles from empty space. It's a magic particle factory. Wrong. There is no such thing as a free lunch in physics. Energy cannot be created or destroyed. If a new particle just flew away into the universe, that energy had to come from somewhere. It didn't come from empty space. The debt must be paid. So who pays the bill? The black hole pays. And this is where the story gets weird. This is the hardest part to swallow. The black hole just ate a particle. The universe, in its infinite accounting wisdom, says that particle had energy. If something eats energy, it should grow, right? If you eat a sandwich, you gain weight. If a black hole eats a particle, its mass should increase. Wrong. And I mean deeply wrong. See, the particle that fell in wasn't a normal particle. It was a virtual particle. Remember, these things borrow energy from the future. They live on a credit card. When the pair was created, the total energy was zero. Positive energy plus negative energy equals zero. The particle that escaped, the one that flew away as radiation, it has positive energy. It's real now. It carries mass away from the black hole. So, if the escaping particle has positive energy, the particle that fell in must have negative energy. This is not sci-fi. This is math. When that negative energy particle crosses the event horizon, it cancels out some of the black hole's mass. It's like adding -1 to a bank account. The black hole eats, but it eats debt. It eats a subtraction sign. Every time a pair is split, the black hole loses a tiny bit of mass. It shrinks. Think of it like an ice cube sitting in the sun. It looks solid. It feels permanent. But molecule by molecule, it is evaporating. The black hole is radiating away its own mass. It is turning itself into light. Now, for a big black hole, this process is agonizingly slow. We're talking trillions of years to lose a single gram. It's a leaky faucet in an ocean. But here is where your brain is going to reject what I say next. What happens when the black hole gets small? What happens when the faucet isn't dripping, but gushing? It turns out, the smaller the black hole, the faster it leaks. And the faster it leaks, the hotter it gets. Wait, did you catch the contradiction? Small things are hot, big things are cold? Let me say that again. A black hole the size of an atom is brighter than a star. This sounds wrong, doesn't it? Normally, big things are hot. The sun is huge and it's hot. A match is small and it's hot, but not sun hot. So why is a black hole the opposite? Why is a supermassive black hole, the monster eating galaxies, basically frozen? And why is a tiny black hole, the size of a proton, a nuclear furnace? Here is the trick. It's all about the curvature. Imagine the surface of the Earth. It looks flat to you. Because the Earth is huge, the curve is gentle. Now imagine a basketball. The curve is sharp. The event horizon of a supermassive black hole is huge. The surface is vast. The curvature of space there is relatively gentle. Because the curve is gentle, the tidal forces, the stretching of space, are weak. Weak tidal forces mean fewer virtual particles get ripped apart. The trapdoor is slow. The radiation is a trickle. It's so slow, in fact, that a black hole the mass of the Sun has a temperature of 0.000000006 Kelvin. That is colder than deep space. It is colder than liquid helium. It is almost absolute zero. It is black. For all practical purposes, it is invisible. But shrink that black hole down. Make it small. Now the curvature is extreme. Space is twisted into a knot. The tidal forces are violent. They are ripping apart virtual particles constantly. The trapdoor is snapping shut faster than you can blink. Pairs are separated instantly. Radiation pours out. The black hole glows. This is where your intuition fails. A black hole the mass of a mountain? It's not black. It's white hot. It radiates X-rays and gamma rays. It's a deadly, glowing ember. And the smaller it gets, the hotter it gets. As it loses mass, it shrinks. As it shrinks, it gets hotter. As it gets hotter, it loses mass faster. It's a runaway train. So far we've learned, black holes aren't black. They leak radiation. They leak because empty space isn't empty. The smaller they are, the faster they leak. Now let's put this into scale. Let's compare a mountain to the sun. Okay, scale time. Do this right now. Hold out your hand. Make a fist. Now imagine a black hole the size of your fist. Is it invisible? Is it black? No. If that black hole has the mass of the Earth, it would be a coin, a tiny glowing coin, and it would be blinding. See, the sun is huge. It has a surface area of 6 trillion square kilometers. It shines at about 6,000 Kelvin. That's hot, but that heat is spread out over a massive area. Now shrink the sun down. Keep its mass, but shrink its size. If you compress the sun into a black hole, it would be about 3 kilometers wide. Its temperature? Basically absolute zero. It's too big. The curve is too gentle. It's a frozen ghost. But what if you took a mountain, say Mount Everest, and crushed it into a black hole? It would be smaller than a proton. It would be invisible to the naked eye. But it would be hot, billions of degrees hot. It would be pouring out gamma rays like a broken reactor. Now, let's go smaller. Take a black hole the mass of a large asteroid, maybe 100 billion tons. It's the size of a single atom, and it shines with the power of 1,000 suns. Because the curvature is so extreme, the space is so warped, that virtual particles are being ripped apart constantly. It's a fountain of pure energy. That sounds impossible until you see the trick. The trick is density. The sun is dense, sure, but a black hole is infinite density at the center. When you pack mass into a tiny space, you curve space-time so sharply that the vacuum boils. It's not just leaking light, it's screaming. So why don't we see these things everywhere? Why aren't we being cooked by atom-sized black holes? Because they don't last. Big black holes live forever. Small black holes burn out fast. They evaporate. And when they evaporate, they don't go quietly. They go out with a bang. Okay, so small black holes are hot. Big black holes are cold. This leads to a terrifying conclusion. Think about this. The universe has been around for 13.8 billion years. If the universe made any tiny black holes, primordial black holes, back in the beginning, where are they? They are gone. They evaporated. See, a black hole is not stable. It is constantly radiating away its mass. It is shrinking, and as it shrinks, it gets hotter. As it gets hotter, it radiates faster. As it radiates faster, it shrinks faster. It is a death spiral. Here is the timeline. A black hole the mass of the sun will take 10 to the 67 years to evaporate. That is a 1 with 67 zeros. That is trillions of times the current age of the universe. To us, it looks like it lives forever. But a black hole the mass of a large asteroid, it evaporates in about the age of the universe. And a black hole the mass of a mountain, it evaporates in a fraction of a second. So, where are the mountain-sized black holes? They are gone. They exploded long ago. But wait. People say black holes destroy information, but that's just a label. If a black hole evaporates completely, if it disappears, what happens to the stuff inside? What happens to the star that formed it? What happens to the astronauts who fell in? What happens to the encyclopedias you threw in there? If the black hole vanishes, does the information vanish too? In quantum mechanics, information cannot be destroyed. But if the black hole is gone, where did the information go? This is the black hole information paradox. It is the single biggest problem in modern physics. It means either our understanding of gravity is wrong, or our understanding of quantum mechanics is wrong, or both. The glitch. We have a machine that deletes the universe's hard drive, and physics says that is impossible. So let's talk about the final moments. When a black hole dies, it doesn't just fade away, it screams. Okay, here is the problem. If you burn a book, you destroy the paper, but the atoms are still there, the smoke, the ash, the heat. If you were a god, you could track every single particle and reconstruct the book. The information is not gone, it is scrambled. This is the core rule of quantum mechanics. Information is conserved. The universe never forgets. But Hawking radiation says, hold my beer. The radiation coming out of a black hole is random. It is thermal. It carries no information about what fell in. If I throw a dictionary into a black hole, and then the black hole evaporates completely into random radiation, where is the dictionary? The mass is gone, the radiation is random, the information is erased. This is the glitch. This breaks physics. If information can be destroyed, then we cannot predict the past or the future. Everything falls apart. Physicists hate this. They have spent 50 years trying to fix it. Here are the theories. Maybe the radiation isn't truly random. Maybe it encodes the information in subtle ways we can't measure yet, like a scrambled radio signal. Maybe quantum mechanics is wrong. Maybe the universe does delete data. Maybe we live in a simulation with a recycle bin. This is the weird one. Maybe the information is stored on the surface of the black hole, on the event horizon itself, like a 2D sticker on a 3D ball. When the black hole evaporates, the sticker peels off and flies away. We don't know the answer, but we do know this. It's not just a puzzle, it's a clue. The fact that black holes evaporate tells us that gravity and quantum mechanics are connected. They are talking to each other, and the language they are speaking is heat. So, let's watch a black hole die. Let's watch the final second of its life, because that is when the universe screams the loudest. This is the end. Imagine a black hole the size of an atom. It has evaporated for billions of years. It has lost 99.999% of its mass. It is now tiny, immeasurably tiny. It is hot, unbelievably hot. As it shrinks, it radiates faster. As it radiates faster, it shrinks faster. It is a runaway reaction. In the last second of its life, it releases the energy of 1,000 nuclear bombs. Boom! It vanishes. But where did it go? It turned into pure energy, gamma rays, neutrinos, exotic particles. It flashed out of existence. And here is the kicker. If the universe made any primordial black holes, tiny ones, back in the Big Bang, they should be exploding right now, today. We should see flashes of gamma rays all over the sky, little fireworks. But we don't. We look, we search, we scan the heavens for these tiny explosions, and we find silence. This is a mystery. Maybe primordial black holes don't exist. Maybe they evaporated too fast. Or maybe they are dark matter. But the theory is solid. Hawking radiation is real. We have seen it in the lab with analog systems, like sound waves in fluids. Black holes are not eternal. They are temporary, and they die violently. But wait, there is one last twist. What happens when all the stars burn out? What happens in the deep future? What happens when the universe is old and cold and dead? When the last star flickers out, the only light left will come from black holes. Okay, zoom out. Zoom way out. Past your life, past humanity, past the Earth. Zoom out to trillions of years from now. The universe is expanding. The stars are burning fuel. Eventually they will run out. The last red dwarf will sputter and die. The galaxies will go dark. The universe will be cold. It will be empty, except for the monsters, the supermassive black holes, the ones at the centers of galaxies. They will be the only things left, and slowly, agonizingly slowly, they will begin to glow. As the universe cools down, the black holes will become hotter than the empty space around them. They will start to radiate. They will shine. In the deep, dark future, black holes will be the only stars. They will be faint, ghostly beacons in an endless night. And then, one by one, they will speed up. They will shrink. They will get hot. And finally, they will explode. The last fireworks show in the universe. And when the final black hole evaporates, when the last drop of energy is squeezed out, the universe will truly be empty. So, the next time you look at a picture of a black hole, don't think of it as a monster. Don't think of it as darkness. Think of it as a battery that will power the universe long after the stars are dead. It's not just gravity, it's the engine of the end, and it's beautiful. Like, subscribe, and maybe, just maybe, don't be afraid of the dark.